Hello everybody, welcome to Guidancee Education channel. We will see the topic that is discussed in this video. We are continuing class 11 physics. Topic discussed is thermodynamics. Under that we will be discussing PV diagram part 2. PV diagram for adiabatic process. Derivation of relation between slope of adiabat and isotherm. Adiabat is the graphical representation of adiabatic process and isotherm is the graphical representation of isothermal process. We will also discuss how to identify an adiabat from an isotherm on a PV diagram. This video will be a little long, but do not skip the video. Watch the video completely so that you get all points clear. That will be of great help to you. If you think the video is useful, do like the video, share the video with your friends who may also be benefited, and also leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now and support me. And also press the bell button and all button for notification of more videos like this. Thank you very much. Come, let us see the topic. In this video, we will discuss PV diagram for adiabatic process. We have already discussed the PV diagram for isothermal process and the significance of PV diagram in the previous video. If you have not yet watched that video, click the I button in order to watch that. For adiabatic process, no state function is constant. Delta Q is equal to 0 because the system is insulated and it cannot exchange energy or matter with the environment. For adiabatic process, P V raised to gamma is a constant. Gamma is a ratio of the specific heat capacity of the gas at constant pressure to specific heat capacity of the gas at constant volume. Variation of V raised to gamma is plotted against pressure. Pressure is taken along the y-axis and V raised to gamma along the positive x-axis. The shape of the graph is a curved line. It is a slope. These are the initial and final volumes V1 and V2. From the diagram, it is clear V2 is greater than V1. That is, volume is increasing. That means the system is undergoing expansion. That is, the system is doing work on the surrounding. So this is adiabatic expansion work. Total work done, that is work total, is equal to area under the graph. We have already seen that in the previous video. That is this whole area. This is the origin, this is the x-axis, and this is the y-axis where pressure is plotted. So this is for adiabatic expansion work, and work is positive. What is the expression for work done? Work done is equal to P delta V. This is delta V. And this is pressure P. That is how we get area under the graph as total work done. Now for adiabatic compression work, or before that, let me make one or two markings here. For expansion work, V2 is final volume and V1 is initial volume. For compression work, V2 is initial and V1 is final volume. So in this case, the initial volume V2 is greater than final volume V1. Compare this with what you got for expansion. They appear to be the same, but for compression, V2 is the initial volume, and for expansion work, V2 is the final volume. So delta V will be negative. Compression work is negative. So in this case, P delta V will become negative work. What will be the shape of the graph? The shape of the graph is the same, but we draw the graph from the initial point to the final point along negative x-axis direction. Note the direction of the arrow. Here also, the total work done is the area under the graph. Okay? When we come to the thermodynamic equation, delta Q is equal to delta U plus delta W. Delta Q is equal to 0. So 0 is equal to delta U plus delta W. So negative delta U is equal to delta W. This is for adiabatic expansion work. That is, when work is done by the system, the internal energy decreases. That is, work done is equal to negative delta U. It cannot exchange heat with the environment. For compression work, work is done on the system. So, negative delta W is equal to delta U. Internal energy increases. Remember these relations. Now compare these with the graph that we obtained for isothermal process. The shape of the graph is more or less the same. Both curves or lines are a slope. But for the same change in pressure, the change in volume is more for isotherm and less for adiabat. So the slope of the graph delta P by delta V will be more for adiabat and less for isotherm. The slope of adiabat is steeper or the slope is greater than the slope of isotherm. Now we will proceed to find the relation between the slope of these two graphs. Derivation of the relation between slope of isotherm and adiabat. For finding the relation between the slope of isotherm and adiabat, we have to derive an expression for the slope of isotherm and then adiabat and then find the relation. We will first derive the expression for the slope of isotherm. Isotherm is a graph plotted at constant temperature. We know PV is a constant. P and V are variables. We have to do differentiation. Since P and V are variables, we have to do partial differentiation. That is, we have to keep P constant first and then differentiate V. Later on, keep V constant and then differentiate P and then add up the two. P dou V plus V dou P is equal to 0. Dou is the symbol for partial differentiation. The right hand side is 0 because differentiation of a constant is equal to 0. From this we can write P dou V is equal to negative V dou P. What we have done is we have shifted this quantity to the right hand side. So we get a negative here. Slope is equal to delta Y by delta X, that is equal to dou P by dou V, which is also equal to delta P by delta V is equal to negative P by V. This is the expression for the slope of isotherm. This expression is obtained from the above equation P dou V is equal to negative V dou P. I hope you were able to understand that. That is by rearranging the quantities. So this is equation 1. Now we will proceed with the adiabat. For adiabatic process, no function is constant. PV raised to gamma is a constant. So we have to differentiate this equation. Since P and V raised to gamma are variables, we have to do partial differentiation. You have to be very careful here because function V depends on another function gamma. So we have to differentiate function of a function. So we keep P constant, then differentiate V raised to gamma, then again differentiate V. Then keep V raised to gamma constant and then differentiate P, then add up the two. That is partial differentiation. We will note down the step. P dou V raised to gamma plus V raised to gamma dou P is equal to 0. Because the right hand side is a constant, differentiation of the constant is 0. Differentiating the exponent is taken as multiplication. So it becomes P multiplied by gamma into V raised to gamma minus 1. This gamma is minus here. Then again differentiating function of a function, we get dou V. We shift the next quantity to the right hand side. So is equal to negative V raised to gamma dou P. Now we will open up v raised to gamma minus 1. Then the equation becomes p gamma into v raised to gamma by v, that is for this minus 1. Dou v is equal to negative v raised to gamma dou p. On the left hand side you have v raised to gamma. On the right hand side you have negative v raised to gamma. So these two quantities get cancelled. So we shift the position of these quantities. Gamma into p by v dou v is equal to negative dou p. On rearranging we get gamma p upon v is equal to negative dou p by dou v, which is equal to negative dp by dv. And what is dp by dv? It is nothing but dy by dx, that is slope of the adiabat. So gamma p by v is equal to negative dp by dv, that is the slope of the adiabat. Let us give it in the right format. Slope dp by dv is equal to negative gamma p upon v. I will mark this equation as 2. Now we have the expression for the slope of adiabat. It is equal to negative gamma p by v. Compare this with equation 1. Both are negative. In the case of adiabat, the slope is gamma times the slope of isotherm. So the slope of adiabat is steeper. That is, it is greater than the slope of isotherm, because gamma, which is Cp by Cv, is always greater than 1. I hope it is clear. We will recall the graph. This is the adiabat. It is steeper than the isotherm. So what have we proved now? Slope of adiabat is gamma times the slope of isotherm. The graphical representation of the isotherm and the adiabat may be given in different patterns, and you may be asked to identify which is the isotherm and which is the adiabat, and whether it is expansion work or compression work. So we will see that also. That is very important. For expansion work, suppose a sample of a gas is expanding by isothermal process and then by adiabatic process. In both cases, the gas starts expanding from the same point. That is, the initial point is same. That is, same pressure and volume. The final point is same volume, but pressure is different. The PV graph or the indicated diagram for the two processes are plotted. From the graph, you can understand the two processes start from the same point and the final point is same volume. We will mark the points A, B and C. We have to identify which of these two plots correspond to adiabat and isotherm. This is normally done by considering the common point and drawing a line parallel to the x-axis at that common point. Consider the angle made by these two graphs from the common line. It should be less than 90 degrees. The angle is marked in the clockwise direction. AC makes an angle theta 1 and AB makes an angle theta 2. From the diagram, you can clearly understand theta 2 is greater than theta 1. Therefore, AB is steeper than AC. So, AB represents adiabat and AC represents isotherm. In the next case, they are starting from different initial points, but the final point is the same. The PV diagram for the two cases will be something like this. The initial points are different, it is at the top, and the final point is the same, it is at the bottom. Points O, C, A are marked. O is the final point, it is same. The procedure is the same, but here we cannot get angle less than 90 degrees at the common point O. So these two lines are extended, that is extrapolated. Points B and D are marked. The parallel to x-axis is drawn along the common point O. The angle made by the two curves at the point O with a parallel is marked in the clockwise direction to get angles less than 90 degrees. They are marked theta 1 and theta 2. From the figure, it is clear that theta 2 is greater than theta 1. So the slope of AO is greater than or steeper than the slope of CO. So curve AO is for adiabat and CO is for isotherm. Now let us see another case, third case. Initial point for both the processes is the same, but the final point is same pressure. In the first case, initial point is the same and final point is same volume. But in this case, the final point is same pressure. The PV graph for the two processes looks something like this. In order to identify which line corresponds to isotherm and which line corresponds to adiabat, we consider the common point. A parallel to the x-axis is drawn at this common point. Points A, B and C are marked. And then theta 1 and theta 2 are marked in the clockwise direction. And the angles are less than 90 degrees. We can understand that theta 2 is greater than theta 1. So the slope of AB is steeper than that of AC. So AB corresponds to adiabat and AC corresponds to isotherm. In all the three cases, you can identify that the volume is increasing in the positive direction of x-axis. So they represent expansion work. Now we will consider three different cases for compression work. The gas undergoes compression adiabatically and isothermally, and their PV graphs are plotted. First case, the initial point is the same for pressure and volume, but the final point is same for volume. Pressure is not same. This is the PV graph for the two processes. Note the direction of the arrow. Volume is getting reduced. We have to identify which is the adiabatic process and which one is for isothermal process. This is the initial point. Angle less than 90 degrees cannot be obtained here. So, just as we did in the previous case, the two curves are extrapolated and the common point O is marked. A parallel to x-axis is drawn at that common point O. The other points are marked and theta 1 and theta 2 are also marked. Theta 2 is greater than theta 1. Theta 2 corresponds to the red line. So the red line is steeper than the green one. So AO represents adiabat and CO represents isotherm. I have noted them as AB and CD. Never mind. In the second case, the gas is compressed from different initial points. The final point is the same. The PV graph for the two processes are plotted. The final point is at the top. There is no need to extrapolate. The angles theta 1 and theta 2, which is less than 90 degrees, can be easily drawn in the clockwise direction after drawing a parallel to the x-axis at the common point. Red colored curve AB makes theta 2 and the green colored curve AC makes theta 1. Theta 2 is greater than theta 1. So AB represents the adiabat and AC represents isotherm. Now we will see the third case. Initial point for the two processes is the same, but the final point is same for pressure only. The PV graph for the two processes is plotted. Note the direction of the arrow. It is compression work. So the volume is decreasing. The initial point has the same pressure and volume. This is the same volume. Here it is same pressure. But the final point has same pressure, this line. Now we want to find out which one corresponds to adiabatic process and which one corresponds to isothermal process. So here we have to extrapolate this. Parallel to the x-axis is drawn at the common point O. AB and CD are marked. Angles theta 1 and theta 2 are marked in the clockwise direction. They are less than 90 degrees. The green line CD makes the angle theta 1 and the red line AB makes angle theta 2. We have to take the angle in the clockwise direction. We have to take an angle less than 90 degrees. These are the points that you have to remember. From the diagram, it is clear theta 2 is greater than theta 1. Curve AB is steeper than AC. Therefore, AO corresponds to adiabat and CO corresponds to isotherm. So when questions of this type are asked, it is very easy to find out whether it is compression process or expansion process by looking at the direction of the arrow. Adiabat and isotherm can be identified by drawing the angle. Hope the video was of great use to you. If you think it was useful, do like the video, share the video with your friends, and also leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now and also press the bell button and all button for notification of more videos like this. Thank you very much. We will meet in the next video with another important topic like this. Till then, bye. Take care.